So today we will be touching upon low frequency vibration techniques or the global dynamic techniques for the purpose of structural health monitoring. In the last lecture, basically what we had done, we had presented a complete synopsis of the entire course, sort of the different types of sensing systems, the various techniques. So it was like a synopsis. Now we will go a very threadbare into each of these, beginning with the global dynamic techniques or the low frequency vibration techniques. So we use the term dynamic with them because they are based on the principle of vibration. Then we use the term global dynamic. Global comes into picture because these rely on the vibration at global level, means entire structure is undergoing vibrations. So when we say the technique local or global, then this is what it means, that the local technique, it acts at a local level, component level. So for example, we have the electromechanical impedance technique. So do you recall electromechanical impedance technique we had covered in the last lecture? So here piezo is used, but piezo is used both as sensor and actuator. So what we do is that we excite the structure through the piezo actuation. So we are exciting the structure through piezo actuation, and simultaneously we are also measuring the current flowing through the circuit. So what we are doing is we are doing the measurement of the admittance Y, which is the ratio of the current to the applied voltage, and both of them, they are sinusoidal in nature. So there is a phase difference between the two. So if the voltages we express in the exponential form like this, sorry, my pen is slipping a little bit, so just bear with that. Then the current will have some phase difference. Sorry, my pen has a slippage today, so just bear with that. So in this technique, basically what we do, we measure the admittance and we measure it across a entire spectrum of the frequencies, so it becomes like a signature. So here we are applying very high frequencies. We are applying very high frequencies of the order of kilohertz. So it acts at a local level because here the frequency is very high and the wavelength of the waves which are generated, they are very low. So that's why it acts at local level. But now the global techniques, they are very different. So global techniques, they can be further classified as either the static response based technique or the dynamic response based technique. So what essentially they mean, we are just recapitulating that in the case of the static techniques, we apply some load, and then imagine that the structure is unknown to us. We measure the deflections. So now we have learned from the our structural analysis 1 that the loads and the displacements, they are related by the stiffness matrix. So essentially from the input and the output, input means the force is applied, output means the displacements. So we have to obtain the unknown stiffness matrix. So that is the working principle of the global static techniques, and it's practically very tough, very tough. Theoretically it looks very much feasible that if we have the output input pair, we should be able to derive the stiffness matrix very easily, but it's not that easy, especially the execution of the experiment itself is very tough. Now global dynamic techniques, they are different. Here we apply, instead of a static force, we apply a dynamic force. So dynamic force application is not very tough. Even if the structure is very huge, we can still make it into vibration. We can still excite it into vibrations. We don't need very high amount of dynamic force. So that's the beauty of the dynamic techniques. So essentially here the structure is subjected to vibrations, and when the structure is vibrating, what we do the measurement of the modal or the structural parameters. So usually what are the modal parameters, we'll see in the coming slides in detail. They are the natural frequencies and the mode shapes, and from these we work out the stiffness related parameters. So feasibility wise, theoretically both the static and the dynamic techniques, they look that we should be able to make use, but from the practical point of view, the dynamic techniques, they are very practical and they are very successful also. So another version of the dynamic techniques is that we start with a finite element model. Let's say we have a bridge, we make its finite element model. Now when we do modeling, our model will never be accurate, because however well we try, there will always be differences between the actual structure and the model. The idealization will have difference, material properties will differ. So what is needed is that we need to update or fine tune our finite element model. That means we have to go to the actual bridge, perform a dynamic experiment, and then from the measurement, what we do adjustment of the finite element model, so that the predictions of the finite element model are exactly matching the experimental results. So this is called as finite element model updating. So this is another version, but essentially in both the techniques we make structure undergo vibration. So you have seen in the case of the small cantilever beams, just we are making them vibrate, and once we are doing the vibration, we are getting the responses, and then we'll see today how do we obtain the mode shapes and the natural frequencies. So basically there are three parts of this topic, and we'll be covering in essentially 2 lectures. The first part is experimental modal analysis. The second part will be the specifically global vibration techniques, and the third part would be integration of smart materials in global vibration techniques. So let's first understand what is experimental modal analysis, and here I have just kept the treatment non-mathematical. Some mathematics is there, but the principles are highlighted so that you understand, and then in the laboratory you will be able to perform. Of course, now the situation is such that only 4 students would be performing the experiments in 2 groups. Both are in different rooms, but rest of you will be getting the data. So what is meant by modal analysis? It is MODAL, not MODEL. So modal analysis is basically process where we identify the structure in terms of its dynamic characteristics. It's very essential signature forming representative dynamic characteristics, the natural frequencies, mode shapes and damping. And how do we do this? We apply an external excitation and we measure the response of the structure at some selected location. So this is how we perform experimental modal analysis. So basically what we are doing is the structure is unknown to us. We may do some prediction by calculation, that will be its theoretical parameters, but if we perform experimental modal analysis, this gives us a true experimental picture of the component or the structure. It could be bridge, it could be some portal frame or any other structure. So this is showing you one setup of the experimental modal analysis. I hope this is now visible to everyone. And now my pen is also active. I can do annotations to make the understanding better. Yeah. So essentially this is the setup for experimental modal analysis. So now here this is typically the sensor, So conventionally, accelerometers are employed in the experimental model analysis, and the output from the accelerometers is fed to a voltage measuring device. Basically, all the accelerometers, they use A to D converter, the digital type. So digital reading is in the form of the voltage. So either a data acquisition system or oscilloscope is storing all the readings. And how do we excite? We need to excite the structure. So one way is that we use a shaker. So what you see here, we have the shaker. So those who have done the course CVL 861, they have seen the functioning of the shaker also in the experiment which we had done in that course related to the soil parameters determination. So shaker can be connected in different ways. So this is one of the arrangement. So here physically there is a connection by means of these stringers. Stringers are basically flexible wires. So in the case of the shakers, there is an actuator kind of component, and this is physically connected to the structure by means of the stringer. So this is one way, and there is another way also. Another way is that we use an inertial form of shaker. So what is an inertial form of shaker? Inertial form of shaker is a bit different. So here let's say we have a pin roller beam, and at the top of this we place the shaker. So shaker is placed on the top, and then we have the stringer. So stringer, we are not connecting to the structure directly, but then what we are doing is that we are installing a plate, and then we are connecting it to the structure by means of these springs. So now what is happening is that when the structure is when the shaker is vibrating, when the shaker's actuator is vibrating, then it's exerting force on these plates, this plate. So this has a fixed mass. So this has fixed mass which we measure, and at the top of this we place an accelerometer. So what we are recording is the acceleration of the plate. So we have the known mass and we know how much is the acceleration. So this tells us how much is the force, inertial force to which this plate is subjected. So the force acting on the structure will be just equal and opposite. So all we have to do is just mass, which is fixed, times the measured acceleration. So that tells us how much is the force transmitted to the structure. Now here in this case, the stringer type, what we have to do in between the stringer and the structure, we have to install an additional sensor, the force sensor. So that's how we can measure the force. So now you see the two are serving the same purpose, but their instrumentation is a bit different. So here we have the sensor sandwich in between the stringer and the structure, and in the case of the inertial type we have a plate, and on the top of the plate we are essentially measuring acceleration. So acceleration measurement is something which is very widely used and very easily available sensor in all the labs. So many labs you will find that force sensor is not available. Then this kind of arrangement using the inertial type of shaker is more practical over there. Alright, so any doubt on this part? Experimental model analysis, the how we are doing, because this is important. So let's say now we excite the shaker into vibrations. So we apply a very simple function. So what we can do is we have function generator in the lab, and we can generate functions of our choice. We can generate simple sinusoidal signals. All you have to do is input the frequency, and this function generator feeds the input to the shaker, and the shaker vibrates at that particular frequency. Or we can also generate a sweep signal. Do you understand what is a sweep signal? Sweep signal means it's a signal like this. Signal like this. Let me just use the eraser to show you more clearly. So this is a sweep signal. So now what can you make out from this kind of signal? Are you familiar with this kind of signal, sweep signal? So sweep signal, what we start, it means that we are starting with a certain frequency. So we have given the instruction that we will start with say 5 Hertz. I'm just giving example, and gradually the frequency will be increased to say 50 Hertz, and we can set a time that, let's say, in 10 seconds the frequency will be gradually increased from 5 Hertz to 50 Hertz. So this is called as sweep signal. So sweep signal is used in the experimental model analysis, so that we are for certainly exciting a particular range of frequencies. We are subjecting the structure to this particular range of frequencies, so that the desired modes, they are excited into vibrations. So it's a very controlled kind of vibration. So we are making sure that in this particular frequency of say 5 Hertz to 50 Hertz, nothing is missed out. Of course, these are just representative. We can make it from 5 to 500 also, and the timing also we can set. So if it's a gradual increase, that gives better results. Okay, so let's say we have done that.
Sir, what is function generator?
Function generator, as the name suggests, you can generate a particular waveform. You can generate sine wave, you can generate square waves, you can generate burst signal. Burst signal means just a single sinusoidal this is a burst signal. Burst signal looks like this, just single wave, only this, rather than continued signal just starting here and ending here. This is a burst signal. Then we can have a square signal also, and we can have the sweep signal you have already seen. So now,
Sir, is it related to any electrical signal?
see, all the
Or it is
signals,
different
everything here is basically digital. Digital means we are getting all the signals. See, in measurement, we always get in the digital form. Whether we are measuring stress, we are measuring strain, everything is coming in the digital form, A to D converter. So finally, that measurement is calibrated. You take any device, any digital device, it may be measuring length, but the output will be in voltage, and vice versa. So basically, we are first generating the voltage signals. So voltage signals are fed to the shaker. Shaker converts those voltage signals to simple mechanical signals. Okay. So everything in the real world, everything is in voltage terms. So basically what is happening, we have applied a sweep signal, and what we are seeing is that, let's say, from time t equal to 0 to, let's say, time t equal to 100 seconds, that is little over 1 minute, we are basically observing this kind of phenomena. So this is basically the response. So we have the response here. So response, what we are measuring in response, we are measuring acceleration. So we are measuring acceleration in meter per second square, and what we find is that this is how the response is varying. That when the time was say 20 seconds, we had an exaggerated response, then it died down. Then at 40 seconds again we had exaggerated response, and so on. So we have in between exaggerated response and then again died down. So what kind of response is this, and what is the reason for this? Can anyone guess what is the reason for this kind of response? So basically, if we are applying a sweep signal, means the frequency is increasing. So remember, we had set that, let's say we are increasing the frequency, I may be using a different values. Let's say let me just change the pen color. So at time 0 the frequency, it started with 5 hertz, and at 100 seconds, let's say the frequency was 100 hertz. So it's increasing linearly. So you can estimate that what was the frequency at 20 seconds. So it will be in between 100 and 5 hertz. So you can estimate, let's say it was just notional value, let's say 20 hertz. So that means at 20 hertz, when the excitation frequency was 20 hertz, there was an exaggerated response, and after that again it died down, and then let's say at 70 hertz here, then again there is an exaggerated response, and so on. So why this exaggerated response is happening? Because these frequencies at which we are seeing exaggerated response, they are basically the modes of vibration. They are the natural frequencies, because we have applied a sweep signal deliberately so that we are not missing any modes in this particular range. So we are basically encountering the various modes of vibration. So these are the natural frequencies. Okay, so to ascertain in a better sense, what we can do is we can just convert the response from time domain to frequency domain. So if we do that, we will be able to identify these natural frequencies in a much better form. So what we have done is, let's say we do fast Fourier transform, Fourier analysis, and in your dynamics course you must have done that, conversion from time to frequency domain. So what we see, something like this, that here we have the entire spectrum of the frequencies starting with say 5 hertz, and here we have 100 hertz. Now what are these peaks? So these peaks, basically they are the natural frequencies. So the frequency domain plot is much easier to visualize, because here we are identifying the natural frequencies more clearly as the peaks. So these are basically the natural frequencies. So this is what the first impression or the first output from this kind of experimental mode analysis, that we are basically identifying the natural frequencies. So all we have to do is, if we have the response, we just convert into frequency domain, and the peaks, they will give us the natural frequencies of the system. So basically, as compared to the time domain plot, frequency domain plot is easier to understand and visualize. Now, what is a mode shape? What do you mean by a mode shape from your knowledge of structural dynamics? So mode shape is basically, in very simple sense, in a physical practical sense, mode shape is basically the deformation pattern of the structure when you are exciting at a particular natural frequency. That is the mode shape. Of course, you understand the mathematical definition of the mode shape from your eigenvalue problem solution. That's the mathematical definition, but the practical definition from the point of view of an experimentalist is basically, it's the deformation pattern at a particular frequency. So for example, at the first peak, if you take the measurements, you will see the deformation pattern is like this. So here the essentially the vibrations, they are happening like this, that this is undergoing this kind of vibrations, slowly reducing and then coming on the other side and increasing to the maximum, and then again going this side. So basically this is the first mode of vibration, and similarly at the next peak you may have the second mode, third mode, and so on. So basically these are the mode shapes. So what we have to do is that we have to make measurements with our sensors to ascertain that what mode is represented by a peak. If it is a peak, first thing is that we have to determine the mode shape at that particular frequency. If it's conforming to some standard or some standard profile, then that is the particular, then we say that it is the particular nth natural frequency. Okay, otherwise we can simply by looking at the peaks, we cannot say that this is the first natural frequency, second natural frequency. We must match it with the mode shape. So if we are seeing any peak, then the best practice is to draw the experimental mode shape, and that will tell us which natural frequency is that. So we'll see and study the entire procedure in this particular course, and in the forthcoming weeks we will be performing the experiments also. Now the other parameter which is of importance is damping. So in modal analysis, what do we measure? We measure the natural frequencies, mode shapes, and then we also measure the damping. So damping we can measure either by the frequency plot, frequency domain, like the left figure is showing the frequency domain response, and the right is showing basically the response under damped free oscillations. So either of the two can be used, but the frequency approach is much better and easier and gives us consistent results. So here what do we do? Essentially, this is the half power band method you must have studied in your structural dynamics. So what we do, we take the peak and we also draw a horizontal line at 0.707 times the peak value. So this is 1 by root 2, that is 0.707 times the peak value, and what we get two frequencies, omega 1 and omega 2. So basically the difference, so this band, so half power band, why do we call this half power band? Because here the energy is 1/2 of the peak energy. So half power band is this, and from these two frequencies, the difference divided by 2 times the natural frequency, we get the damping ratio. So this damping ratio, what happens if we have multiple peaks? Then if we have multiple peaks, it is possible that we have different damping ratio corresponding to each peak, because these are different modes. So damping is something, it is not uniform. We cannot assign a very consistent and uniform value of damping for any structure. It will definitely show variation. So if you choose a peak, you will get certain value of the damping. You choose another peak, you will get another value of the damping. The other way is use the logarithmic decay plot. So all we have to do is that you just make use of the 2 consecutive peaks, and from these you can obtain the damping ratio the way it's illustrated here. So these things you have already learned in your structural dynamics course, so I have just kept them brief for recapitulation purpose only. Now I define another term called frequency response function, but before that, if you have any doubt, just raise your hand. So no doubt, so let me define frequency response function. So frequency response function is basically ratio of the output to the input. So what's the output in a modal test? Output is the response. So we are most of the time measuring acceleration, or we are measuring displacement, or maybe strain. If we are using piezo sensors, then what we are measuring strain. But otherwise we are most of the time measuring acceleration directly, because acceleration measurement is something which is most practical. Even if we have to obtain displacement, still we have to measure first acceleration. Then acceleration, once we measure, we have to convert into displacement. And how do we convert? We make use of the relationship that velocity, what is velocity? It's basically first derivative of displacement, and what's acceleration is the second derivative of displacement. So that way we use acceleration to derive either the velocity or the displacement. So basically frequency response function, it is defined at a particular point. So it is the ratio of the response to the force applied, because what we are doing with the shaker, we are applying some force, so that force has to be measured, and then the response also needs to be measured, and the ratio of the response to the force, that is the frequency response function. So it is at a particular frequency. So if we are dealing with a range of frequency, then we must have multiple points. So then we obtain a particular plot. So that is the frequency response plot. So now let me ask you a question. In general, if you are applying a force, let's say you are applying a force, and this is how the force is varying with time. Let's say we are using a sinusoidal function, or if we shift our reference here, then it is a cosine function. So either a sine function or cosine function can define a force. Now coming to displacement, if we are let's say measuring the displacement, you will find that force and displacement, they will have a phase difference. So what is phase difference? First of all, what do we mean by phase difference? So I am using red color to define the response, the velocity. You will find that the displacement will inevitably lag behind the force. So if that means that the peak force is coming at particular time, peak displacement will be lagging behind it. So what is this called? This is called as phase lag. Alright. So why is this phase lag there in structures? And any guess or any comment why this kind of phase lag happens in structures?
Because of the huge mass of the structure.
Mass. Okay, any other comment? Basically, if we are talking of only displacement, then what happens is that force and displacement, they have phase difference. If the structure is a pure spring, it does not have any inherent damping, it does not have any mass, then there will be no phase difference between force and displacement. They will be in phase. But because we have finite mass and finite damping, so that's why there is phase difference. Okay. So these are the reasons for phase difference between the force and the displacement. So because of the phase difference, what happens is that we make use of complex functions. So what we do is that we represent the force by a phasor diagram. So now imagine that this vector, what is a phasor? Phasor is a rotating vector. Let's say this is the magnitude, F0 is the magnitude of the force, and this is rotating at the angular frequency omega. What is omega? Omega is the frequency of the force. So we say that at any given time, the horizontal projection, the cos term, this is the force, this is the real part of the force, and the imaginary part is the sine term. So if we are using cosine function, then cosine function is basically the real part and the sine function is the imaginary part. So basically the horizontal projection, so imagine this is a rotating phasor and its projection on the x-axis, that gives us the value of the force at a given time. So basically the rotating motion is converted into this kind of sinusoidal function. Okay. So we can represent it like this, but let me just first erase this part so that you are able to see it clearly. Yeah, so what we can do is that we can represent the force, the phasor, like this in complex terms. So the advantage of complex terms is that it helps in quick calculations. So we have this force we say that it has two components. One is the real part and the other is the imaginary part. So basically we are representing it like this in a very compact form. So of course, what is the real part, what's the imaginary part? Basically we say that the real part is the cost component and we are ignoring the imaginary part. Okay, or we can do the other way also. Either of the two we can consider and we can ignore the other one. Okay, so if we are doing in this fashion, then response can also be expressed in similar phasor terms. Only thing is that response will lag behind the force. And response could be displacement, it could be strain, it could be acceleration. So we are just using a general term R for response. So now response is lagging behind the force. So we can represent it in the same fashion like this. So this is the response phasor and its horizontal projection is R0 cos omega t minus phi, because phi is the phase lag here of the response as compared to the force. Now you see the beauty here, why we are using the exponential functions, that it makes everything very compact and it takes into account the phase difference very easily. That's why we have used the exponential functions. So all the calculations which result from this, they become very simplified. So all we have to now use is the definition. So what is the frequency response function? But before that we have already understood why there is a phase difference between the force and the response. It's because we have combination of the damping, mass and spring. So when these terms, especially the damping is there, then it brings phase lag. So basically now we can define the frequency response function. So we substitute here the instantaneous values and we get this kind of result. So basically this is measured at a particular frequency. So we are measuring it at a particular frequency. So if you measure it across the entire range of frequency, you will get a plot. So the plot will just show in the next slide, but first let's see what is the relationship between displacement, velocity and acceleration. And it's very easy if you use exponential functions. So displacement, let's say this is the displacement with the phase lag. Now what is velocity? Velocity is basically the first derivative, and you can very easily use your knowledge of the exponential and complex numbers to write it like this. So what we see here, we see that if you see the phase difference between the displacement and the velocity, velocity basically leads the displacement by how much phase angle? 90 degrees. Understood? And similarly, if you see acceleration, acceleration is the second derivative of the displacement, and here you can always express it like this, that the acceleration will lead the displacement by a phase angle of 180 degrees. And all these, they are interconvertible. For example, if you are measuring acceleration, how do you convert it into displacement? Very easy. You see the expression. In the expression for acceleration, what is different? We have omega square. We have omega square here. That's the only difference. Of course, there will be minus sign also. But essentially, if you are measuring the peak acceleration and you want displacement instead of the peak acceleration, all you have to do is find out how much is the frequency of vibration and divide. Then you will get displacement. So they are interconvertible. Usually we measure acceleration and then we can obtain either the velocity or the displacement. So if you want to obtain displacement from acceleration, just divide by omega square. If you want to obtain from the displacement the velocity, then you just multiply by g omega, and you can also obtain velocity from acceleration by divided by omega. Okay. So now in general the frequency response function appears like this. Now this is measured across the entire range of frequency. We have started with 0 and let's say we have 100 Hertz here. So in this range we have the frequency response function. So what does this signify? It signifies that if we have a particular frequency, say 25 Hertz, then at this frequency what happens is that if you are applying unit force, then the response will be this much magnitude. So it is basically the response per unit force. So that's what's implied by the frequency response function. So if we are given a particular force and its frequency, you can very easily obtain from the frequency response function what is the expected response of the structure at a given point. So now when we say frequency response function, now there are two terms here, the force, input force, and the response. They may be measured at same point or they may be measured at different points. For example, here we are applying the force at point J and we are measuring response at point I. So the two are different. So this is the input time force and we convert it into frequency domain. So we have the input spectrum, and then if we have the frequency response function with us, then you know that at a particular frequency all we have to do is, this is the force as a function of frequency 0 to 100 Hertz for example. And what does this show? This shows the force frequency domain, and we have the frequency response function also 0 to 100 Hertz. So you know that for unit force at a given frequency, what is the response? Unit force, this would be the response at this particular frequency. Let's say this is 50 Hertz, and you know that the input force at 50 Hertz is some value. So all you have to do is just multiply with this and you will get the response. So this is the output response just by using the relation that your frequency response function, we generally use the symbol H. H is basically R by F. So here we have H given, we have F given, so we can calculate what is R frequency wise. So this is the output, and then we do inverse Fourier transform and we get the output time domain response. So this is how frequency response functions, if we are available, we can make use to obtain the response of the structure to any time history. So it is used for experimental time history response prediction. Okay, so any doubt till now? We'll end here and we'll continue from the next class. But if you have any doubt so far, please let us know.
Sir, can you repeat the last part?
You mean this slide or the previous slide?
Yeah, this slide.
Okay, let me just erase everything. Oh, sorry, it's not erasing. So frequency response function, we have defined that frequency response function is the ratio of the output to the input or response to the force. So H we define, so we use the symbol Hij. I stands for the point at which we have measured the response, J stands for the point at which we have applied the force. So basically Hij is your response measured at ith point and your force applied at jth point. Alright, now it could happen that I and J, they may be same point. It's feasible. So basically if we are having at our disposal the frequency response function, then how do we make use to obtain the time history of the displacement for a given force time history? Let's say we are given time history of the input force. So input force is applied at this point J, and we are given this time history, an arbitrary time history. So what we have is, we have the frequency response function for these 2 points I and J. So let's say first step is that we do its Fourier transform and convert the input force into this kind of input spectrum, frequency domain, just say 0 to 100 hertz. And then if we have the frequency response function available with us, then how do we use it? We have to use it frequency by frequency, because input spectrum is from 0 to 100 hertz. The frequency response function is also from 0 to 100 hertz. So one by one we make use of this equation. So how do we generate response? So response is basically, just take it on the other side, Hij into Fj. So at each frequency what we do, let's say at this is the frequency response function at say 50 hertz. So we know what is the value here. So we just multiply this with the force at 50 hertz and we get the value of the displacement at this particular frequency. So let's say we have got this value at 50 hertz like this, and similarly you measure, you do this calculation at each point, and finally we will get this kind of plot. This is the output spectrum. So that is the response at this particular point in the frequency domain. Now if you have to get into time domain, just do inverse Fourier transform. Just like we have the Fourier transform, we can do inverse Fourier transform, and once we have done the inverse Fourier transform, we will get the true response at that particular point. So
Sir,
I'm just
does
erasing this.
response mean
I'm
deformation?
just erasing this. Yeah. So this is the final output. So what we have done is we have made use of the frequency response function. Yes. Any doubt?
Sir, does the response means deformation?
It means the way you are defining the frequency response function is basically using two things: the response and it's using the force. So response in the case of the modal analysis most of the time is acceleration response, or if you convert acceleration into displacement, then it's the displacement response. So we don't use the term deformation here in the modal analysis. We use basically displacement, acceleration, or velocity. Alright.
So that means we are using a response word for displacement, acceleration and velocity for all of the three.
Any response, it could be strain also. Anything, any parameter you choose, that will be your response. It can be even the curvature. So when you are understanding the term frequency response function, just be open. Frequency response function can be measured with respect to any parameter of your choice. Alright. Any other doubt?
Yes, sir.
We'll continue in the next class from this point. Frequency response function, and once we have defined the frequency response function, we'll tell you how do we get the mode shapes, because so far you have learned the concept of mode shapes solving the eigenvalue problem. You have only mathematical knowledge, but now we want to give you the practical knowledge. What is a mode shape? So we are using the practical definition. It's the basically the profile of the structure when it's vibrating at a particular natural frequency. Okay, any other doubt? Just raise your hands, and we have time. We are going very slow. We don't have to rush because our course is running in smooth sense.
So the FRF is independent of the position we are using for forming FRF. Like for a particular position, we are measuring response also and the applied force, right? And we are just varying the frequency. So if we change the location of input and output, the RFR will be same.
No, it will be different. It is very much
So
point
we
specific.
So the FRF we are using it is for jth location. We
Yes.
already have
Exactly. The frequency response function has to be defined. It is for a specific set of locations I and j. That's why we are using hij. That is, we are dividing the response at the jth location by force applied at the ith location. Okay.
Okay, sir.
All right. Any other doubt?